Good day, my name is Caspar from Eindhoven University of Technology, and today I will present to you our work into physics-driven trajectory stitching. Modern research and society leverages increasingly on high-fidelity pedestrian tracking techniques. These techniques make use of tracking sensors like the one in this picture and which are mounted to the ceiling and look in downward direction. From the area underneath the sensor, they create a depth map, and from the depth map, we can anonymously localize all the individual pedestrians. Now let me give you an example of a train station in the Netherlands, Eindhoven Central Station to be specific, where we have a measurement setup using 20 sensors to continuously monitor all the pedestrian movements at this platform. Now from this animation we can see that we can monitor and track all the pedestrians, and we can see all the interactions between the pedestrians. Now at this moment in the animation we can see that a train has arrived at the platform and people start to leave the train and find their way towards this stairs and escalators. Now in order to analyze the usage modes and the interactions between the pedestrians, the dream is to have full trajectories from origin to destinations of every pedestrian. So to do this research, it is crucial to have high quality data. In our contribution to Pedestrian Evacuation Dynamics conference from last year, we already made a benchmark for modern high-fidelity pedestrian tracking systems. So in this research, we did a couple of tests to see what the current state of the art is in pedestrian tracking. So we did the experiments for this contribution from last year, and the first experiment was a line-based crowd flux estimation. So we wanted to determine how accurate a pedestrian tracking system can count pedestrians crossing a line. The second test was a global density estimation, in which we wanted to know whether the system was also capable of determining a correct amount of pedestrians inside a predefined area. The third test was individual position detection, where we wanted to know if the system could accurately detect the location of all the pedestrians. And these three first experiments all proved to be very accurate. However, our first test, where we wanted to determine the tracking consistency of our setup, turned out to be less accurate as expected. So in this specific test, we asked participants to start in one of these areas and walk to one of the other areas. So this way we could know the ground truth origin and destination of every trajectory, and we could determine if the trajectories completely followed the path from origin to destination. And in this instance, we can see that from the 10 trajectories, 3 were inconsistently tracked from origin to destination and were interrupted somewhere in the middle. Now let me give you some examples of inconsistent time tracking. Again, we look at the same platforms before, Eindhoven Central Station, and in this figure we can define areas where we expect people to originate or destinate. So this yellow area is the boundary of our floor field where we would expect the start and end points of all the trajectories. However, if we have a look at all the origin and destinations, we can see that almost half of the origin and destinations are inside the floor field at locations where we wouldn't expect them. Now, for instance, we can see that this is the result of tracking errors, where the sensor was not capable of recognizing that two trajectory pieces actually belonged to the same person. An example of this is also by occlusions. If an infrastructural object like the sign you can see in this figure occludes the view of the sensors, we can see that there will remain two trajectory parts, and the part underneath the object, underneath the occlusion, will not be tracked. So the big challenge is now how to improve this tracking consistency. And maybe the first answer to this question would be to improve the measurement setup or the tracking algorithm. However, in reality, this is not always practical or feasible because we cannot completely redesign our tracking setup and remove all the infrastructural objects that obstruct our measurement system. And we can also not completely retrack all the already recorded trajectories. So the second answer could be to restitch the trajectory pieces. And in this example, we can see an incoming trajectory piece and 3 possible continuations of this first trajectory piece. The big question is now, which of these three continuations belongs to the same person as our initial trajectory? Because we need to run this restitching algorithm only on the already broken trajectories, we can do this computationally way more efficient than completely retracking all the trajectories. So we identified two classifications of broken or interrupted trajectories. The first, on the left, is a trajectory where we miss a piece in the middle, and the second is the classification where we have a duplicate piece in the middle of the two trajectory pieces. We want to identify and reconnect both classifications, and we want to do this with also very accurately for high densities, because you might imagine that doing this for one trajectory can be very easy, but doing it for many is very difficult. And again, we want to do it computationally inexpensive. Because we already do it only on the broken trajectories and not on our full dataset, we can do this computationally less expensive than the full retracking algorithm. So we need for this retracking algorithm two ingredients. Let me show you this trajectory where we have in blue the initial trajectory and in orange a possible continuation of our trajectory. And the first ingredient we need is an extrapolation policy to see how the end of our first trajectory can be extrapolated in space and time in order to see where it would end up after some time dt. The second ingredient we need is a distance metric. In this distance metric, we need some measure of the distance between the end of our extrapolation and the beginning of our possible continuation. Let's look at the first ingredient, the extrapolation policy. So we look at the final position of our initial trajectory and we want to extrapolate this in space and time. And the most simple and straightforward way to do this is a linear extrapolation where we take into account the velocity at the last point of our trajectory and we extrapolate that linearly in time. We can increasingly make this more complex by adding first some acceleration. So we take the acceleration at the last position of our initial trajectory, and we can make it more complex by even taking into account repellent wall forces. This is a first attempt at implementing a social force pedestrian model to extrapolate our particle. The second ingredient we need is a metric. This metric is a measure to define the distance between our extrapolated particle and the possible start of the possible continuation of our initial trajectory. So we need to find a measure that defines the distance between these two points in space and time. We propose to use this metric, which is a linear combination of the length distance and the velocity distance. So we see that we have the distance in space and a mismatch in velocity between these two points. Let's now look at the second classification of interrupted trajectories. This classification has two trajectory pieces which have a duplicated trajectory piece in the middle. Please note that we do not need an extrapolation policy in this case, because we already know the location of the trajectory at every point in time. So we can directly apply our metric, which is this linear combination between the distance in space and the mismatch in velocity, and we apply it to the last point of our initial trajectory and the point of our possible continuation at the same time point. So now we have all the ingredients needed in order to restitch our trajectory dataset. So let's have a look at how this works in practice for multiple trajectories. So we have initial trajectories A and B on the left, and we have possible continuations C and D on the right. So let's start by extrapolating our trajectories A and B. Now we have 2 points, extrapolated points of both initial trajectories. The next step is to apply our metric. First we do this for trajectory A, and we can see that we have possible continuation C and possible continuation D. We do the same for trajectory B, and we get four values for our metric. Now we want to analyze these metrics and minimize the total stitch distance. So we want to minimize the value for the combination of our two stitched trajectories. This helps us to find that the best combination of stitches will be A to C and B to D. Now let me show you what the effect is of our stitching algorithm on the dataset at Eindhoven Central Station, which I showed you before. This is again the figure of origins and destinations before the stitching. Now after applying a stitching and a cleaning algorithm, we can see that we drastically decreased the number of origins and destinations which are at unlikely positions in our measurement domain. However, the big question is, did we stitch the correct trajectory pieces? So therefore we create a benchmark for our stitching algorithm. The first part of our benchmark consists of our experimental data sets, which we collected during our collective dynamic contribution from last year. So we apply our trajectory stitching algorithm on these trajectories, which I showed you before. The second part is an artificially broken trajectory dataset, in which we take all original trajectories, of which we know they originate and destinate at viable locations, and we manually, artificially break them into the two classifications. So either missing a trajectory piece in the middle or duplicating a trajectory piece in the middle. We can do this for different time gaps, and we are doing this in our benchmark for time gaps ranging from 0.5 to 6 seconds. Now let's have a look at the results. So first, experimental data set. You can see again that we have this experimental data set with 10 trajectories, of which 3 are broken. We apply our stitching algorithm, and we can see that the 3 broken trajectories are now all continuously tracked from origin to destination. We did this for all 7 experiments which we conducted among 2 different measurement setups, and for the linear extrapolation we can see that we initially had 75% accuracy, and after stitching we have 90% accuracy. We do the same for the quadratic extrapolation, and I want to note that there are no walls in this domain, so this was the same for the model-driven extrapolation, and we go up to 91%. However, we want to check it with no extrapolation at all to see if the extrapolation actually makes a difference, or if we can just take the metric between the 2 trajectory pieces. And we see in this experimental data set that there is no difference between no extrapolation and the other 2 extrapolation policies. So apparently the simpler case is working better. Now we continue with the results for the artificially broken trajectory dataset. Let me remind you, we start with originally complete trajectories, which we break artificially into the 2 classifications. We can do this with different time gaps. This allows us to create a graph of the time gap versus the accuracy of restitching. And we can see that for small time gaps, the different extrapolation policies all perform the same. However, if we go to larger time gaps, the extrapolation policies will have a higher accuracy than no extrapolation policy. And strikingly, the simple extrapolation policy performs the best of all the proposed extrapolations. So in conclusion, I've presented to you an algorithm to reconnect interrupted trajectory pieces. I've proposed 3 different extrapolation policies, and we have learned the lesson to keep it simple. We also presented to you a benchmark to test different policies, metrics, and parameters of our stitching algorithm. So the outlook will be to perhaps study different distance metrics and maybe implement our stitching methods directly into the tracking algorithm for future pedestrian measurements. I want to thank you all for listening. I'm open to all your questions, and I would like to invite you to Pedestrian Evacuation Dynamics Conference next year, which will be hosted by us at Eindhoven University of Technology.